started. My name is SANJAY DORAIRAJ, and I'm with Comcast, and my colleague KHEM is also here with me. We're going to be talking about the lessons learned in terms of moving the RDK software stack, I'll talk to you about it, to the Yocto OE platform. I guess a lot of you folks know KHEM here, so KHEM has been like a key part of that transition and has been like the architects of the whole transition for us. So the plan right now is the idea is to educate you on all that has been done, from a Comcast side and from the RDK industry side. Hopefully if you're going to be working on the RDK software stack, then there'll be a lot of useful takeaways for you on how to work with the RDK software stack, just to make your life easier, as well as also the tooling involved in trying to make easier to ease the development process and the release process and all that stuff. So if you have any questions, just feel free to stop us at any point. So we'll do an overview of the RDK. We'll go look at the software stack itself. We'll talk about the older build framework that we had from where we transitioned to Yocto OE, the challenges with that build framework, and what was involved in moving to the OpenEmbedded build framework. Some of the challenges there that we encountered just working with the various vendors and access control and working with developers and trying to overcome developer inertia in terms of working with older build systems. The tools that we had put in place in order to kind of orchestrate the entire build process. We worked with several thousands of developers work on the RDK software stack, and we worked with at least 15 OEMs and a bunch of software vendors. So trying to get all of that machinery going, it requires a lot of tools, especially when all of these vendors are competing with each other. It's not an entirely open source in that sense, because here you have competing vendors that are trying to take part in the process. So we need to make sure that there is sufficient isolation across all of them. And some of the features that are coming soon to the RDK software stack. So RDK stands for the Reference Design Kit, and essentially just a name that stuck. It became too successful too fast that we didn't really have time to listen it and give it the name. It was called the Reference Design, and it just stayed there. And now everyone calls it the RDK. So development started in 2012. It started off as a more skunkworks type of project where we were trying to see, if the concept of a cloud-based guide would work. And a cloud guide essentially means, well, rather than have a native guide on the set-top itself, the idea was, what if we had a cloud guide where every single remote control instruction went to the cloud and came back. And in addition to the stuff that came back would be like drawing primitives and images that would tell you the commands telling where certain stuff should get placed. So that was something that we were experimenting in 2012, and we worked with Intel and Pace on trying to come up with a proof of concept for that. But then the proof of concept became people saw the way that the guide was, and obviously the Comcast, the guide that we had at that time was very it was not a very pleasant experience for users, given that times had changed and Netflix and other companies had much better user experiences. So they essentially pounced on this guide, and they decided to kind of take this out to every single device. So initially we had a build script that was 5,000 lines long, and then because we really had no clue that that we would have to take this out to other devices. But then as it became clear that we had to roll it out, we started coming up with our own build framework to kind of refactor things and try to make it a lot easier to work across multiple vendors. The RDK is managed by a company called the RDK LLC, which Comcast, Time Warner, LGI, and other cable companies are part of that. And there are close to 200 members that license the RDK software stack. The reason, there is a push right now to open source the RDK. The reason why we originally didn't really want to get it out there was because we were still new to the whole open source, the concept of open source, and just trying to tread lightly and understand what the risks are. But as we matured, right, and we kind of understand the advantages of open sourcing software, we are moving in a direction to try to open source this. soon. So right now we have like around 200 members who are part of the RDK LLC, and they're actively participating in the RDK. And Linaro is one of those members. It's a software stack based on Linux. Obviously, that's why we're here. And it's the platform for the Comcast X1 experience. So one of the main the advantages of of the RDK software stack is that it is the fact that it is so simple, right? That there's no complexity on the setup itself has made it much easier for us to roll out our cloud-based solution across our entire footprint. And Comcast, to put things in perspective, we have around 45 to 50 million set-tops out there, and we are hoping that, and right now we have more than 5 million set-top boxes that run the RDK software stack, and we're hoping that in time we will roll it out to every single set-top that is out there. This is just a high-level overview of the software stack. So if you see, we have the SoC and OEM pieces that come in, and then we have the RDK piece, which essentially has the biggest pieces of that is a media framework and a graphics framework. So the display stack is right now is mainly Qt WebKit based, and the media framework is based on GStreamer. We have plans, and we talk about some of that today and other sessions, where we do want to move to a display stack that consists of Wayland and C and the Chromium CEF framework. So that's kind of where we want to move to. We're also generally headed in the direction of ARM. So most of our setups that are coming up, at least on the client side, are moving in that direction. Although we do have a large set of folks on MIPS as well. So in terms of the components, those are the two main components. And then the MVPD are essentially the parts that come from the cable companies themselves, like the cable guides and all of that. So that's where they fit in on top. Some companies have a native guide on the RDK, some don't. And Comcast doesn't, whereas Time Warner may have a native guide on the RDK. So it depends, but the RDK facilitates both models. We'll next talk about some of the motivations for the build framework. Like I said, this stuff, like it just happened very soon and very fast, we had to try to figure out a way by which we could put things under control. And at that time, Yocto was really not on our radar. I mean, we didn't really know about it. We were not like build experts, all of us. And we really didn't have that connection to the open source community to kind of know what was the best out there. So we decided to build our own build framework. It was based on Python, and essentially it was a means of orchestrating the entire build process and generating images that could then be deployed on our set-top boxes. It consists of being able to build like on a component by component basis, because before we had monolithic build scripts, and the idea was to refactor them. And it allowed for very strict access control so that you had that separation between vendor proprietary code, and then we separated out the fetching of code from the building of code, because a lot of times people were surprised when they built something, and if you had a statement in there where they're trying to do a git fetch operation or something like that, then we found that kind of stuff happened under the covers, and they were not sure like why things didn't work as expected. So we intentionally separated the two. The user first does the build, and then he first does the source code fetch, and then he does the build. Some of the technical aspects was written using Python. We use G-Client, so we heavily relied on G-Client, and now with the new framework we're on repo. We use Nexus repository for storing binary artifacts, so make sure that we never had any binary objects or blobs inside SVN or Git. This is just a high-level diagram of that picture of the legacy build framework. So you have source code and binary repositories, and you have the workspace setup. And once that is done, then you went to the build phase where you had environment setup, component build, post-processing. You could do additional stuff like stripping symbols and things like that. And then you had the final image generation. And you had a bunch of artifacts that got generated, like binaries, documentation, logs, and statistics. So the challenges with that system were, one of the bigger challenges was scalability. Like, how do you scale this in order to accommodate new vendors, new OEMs, new SoC vendors, and more developers, right? So that was like a huge challenge that we had. And so what we found was that we were really not experts. Our core competency was not building a build framework. That was certainly not what our core competency was. And as we started working with more vendors, we encountered more and more issues and pushback from vendors because they were able to justifiably convince us that there are certain issues with the way that the build framework worked. So we started looking for another framework, like open source that would essentially be a replacement. The other issue was maintainability. I mean, again, going back to the fact that we were not build experts, right? We needed someone to grow and maintain this build framework, and we didn't really have that expertise. So and moving to Yocto was like a good choice because you had something that was very actively maintained, right? And you had something where you have a bunch of experts out there who are available to help you with any issues that came up. And then our build framework was not standards compliance. The artifacts that were generated or the file system hierarchy, any of that, there was really no strict control around how things happen, right? Like you could have intercoupling between different components, and Nico knows a lot about that. He was part of the original team that helped us move to the new to the OpenEmbedded framework. So you could have issues like intercoupling between components, and you could have used any build system to build, and it would just work because it was more like you just take this thing and shove it in, and it would just work. But it really wasn't the right way to do things. Where you're especially trying to come up with something that's best in the class in the industry and working with different people, you really didn't have a way to convince them that this is the way to go. Build consistency is a big thing. Like every time you build, you could get different results. In some cases it could fail, and then even if you do clean up the workspace, in one case it would fail, in some cases it would succeed. So there really wasn't that consistent deterministic experience out of a build. And performance was also a bit of a problem. There weren't things like estate caches. We had our own pre-built management system, but again, it was proprietary and it wasn't really the best. So builds used to take a very long time. And a lot of times, vendors, there really wasn't a way to force people to leverage all the CPUs. Like you would have some folks like hardcore -J4 or -J8 and really not allow us to automatically leverage the benefit of the CPU. So there were a lot of issues with build performance that we had to deal with. And also collaboration, like a way where one or two people could work with each other. The idea of layering that comes through Yocto, right? That really wasn't something that was very obvious with the RDK build framework, and people had trouble trying to work with, especially as OEMs and software that tried to do stuff separately. Turned out that they had to they were stepping on each other's toes. Like software vendors would provide their artifacts to the OEMs. The OEMs would then patch those and then push them up, right? But there wasn't that, the isolation was not there. So there was a lot of this dependency that caused a lot of breakage later on. And obviously the documentation and knowledge base was a problem because we were writing our own documentation and things were moving so fast that the documentation didn't keep up. So there really wasn't that, that consistent or accurate documentation as well. And obviously, having a proven build system, right, makes a big difference as well as a common framework. Okay, so I'm going to turn this over to KHEM now, and he's going to talk about the magic he worked at Comcast.
Yeah, hi. So actually, it started with Linaro at Comcast. I'm a long-time OpenEmbedded developer, but I didn't start it at Comcast, and it was actually a project that was started with Linaro and Nico and his team, Trevor, and was worked there before. What we did thereafter is we brought that into the product. So I'll cover some of the challenges we saw taking it from an emulator-based BSP to really deploying it onto a real X1 device, and it was a long journey. So we have layered architecture because, as Sanjay mentioned, we have ACLs for our OEMs because they want to share across their components, but we want a horizontal view of the stack at the same time. So we want to control the same piece, right, for a different vendor. So the layer architecture gave us that flexibility where you could have layers, where you could allocate specific layer to a specific OEM, give them the right ACLs, and when you build for a given platform, you would still get a consistent view. So it was a very strong feature that we have leveraged quite a lot. Repository structure cleaned up because we could, so Comcast did have an existing structure which was pretty well thought out, but there were problems with that because what we do is we take certain pieces which are generic, and then we take OEMs of specific pieces, merge them together, and then that becomes our view for a given component. And so that architecture did fit in with OpenEmbedded quite well by having multiple source fetches for different pieces, and then giving a uniform view and for the component. So we had to do some of the repository structuring for in order to meet this kind of scenario. So we, in some cases, in RDK, this was not consistent, whereas in Yocto we expected it to be consistent, and there was restructuring involved or refactoring of repositories. So we have actually used the Android repo tool for doing the workspace orchestration, and this was a big step. I'll cover a little bit later on how we are using repo. Actually, we have enhanced repo internally. We have written plugins that allow us to achieve our workflow. Earlier Sanjay mentioned that we have this fetch and build model, and Yocto and OpenEmbedded, we don't do that. We fetch as we go. So that's a very disruptive for developers in general, because developers want a consistent view of their source code. So they don't want you to be fiddling with the source code when they have a view and then they want to use that consistent static view. So it's more for the developer angle. For the integrator point of view, it doesn't really matter. Integrator needs an end-to-end builder. It doesn't matter from where the source code is being fetched, whether it is being fetched, it doesn't matter. But developers, they are very sensitive to how their sandboxes look, because they are changing them and they don't want anything changing underneath without their control. So we have to tool in repo quite a bit to achieve that goal. So what we have done there is we have actually used the external SRC feature of OpenEmbedded. So external SRC feature is, what it does is it tells BitBake that it should not be fetching the sources, but I have the sources already prepared and they are here. And then the fetch step and unpack step and patch step, they are all shunted. So what we did with this one is that all the components are now mentioned in the repo manifest. So our manifest mention all the RDK components, like you've seen Android or somewhere. Everything is checked out as a static into a repository structure, which is matching to our traditional RDK build. And repo has then post-processing hooks, where it generates the Yocto configuration metadata to tool in BitBake to actually look for those particular components in those checked out source streams. And so this work is under progress. We have finished it for a few devices, but from here on it's just a application, but conceptually it is proven to work. So we initially check out, when you create the workspace, everything gets checked out except your BSP. And BSP is most of the time pre-built. And all the RDK components are checked out, like your traditional workflow. So we have tried to solve the OpenEmbedded being more an integrator's tool than a developer's tool problem. it has been received well by the developer community in the sense that they get it, that it's just another build system instead of make file. Instead of make, there is bitfix, which is more of a pseudo builder or meta builder, if you will. So that's what it was involved with the repo integration, and soon this manifest will be actually available on RDK LLC, I think in the next release, whenever that happens, which I think they are preparing right now. So one of the steps we did there was that all the RDK components, we wanted to give more of a consistent view at the component level. So right now, if you look out there, the previous release of RDK, then some of them have make files, some of them have shell scripts to build them. Each component has its own story. That's not a limitation of OpenEmbedded, but we wanted to have a consistent component build model, and so we had actually taken a lot of efforts to deploy auto tools into every RDK component. So if you work with RDK, you will have and if you have worked with auto tools, then you will have a familiar view of the components.
What it did benefit us with is that our OpenEmbedded recipes for these components are very simplified because of that, because all the complexity is now encapsulated into the auto tools, and it's now delegated into the components as a responsibility, because they build the component, they know how it should be built, and OpenEmbedded orchestrates it from the top. So the intricacies of this should be built that way, this should be built this way, from a complete system builder is now divided into individual components. So that's one change that we have done with this. So binary management, essentially, Sanjay did mention about that. There were these binaries that were being generated in the previous build method. Here, we had to do some of restructuring in how OpenEmbedded generated images. So RDK has a certain set nomenclature, and it's hard-coded into the firmware. So images has to have certain strings, and it has to be less than, I think, 48 bytes or something, 64 bytes. And so our image names have to be in certain sense. They have to be encoded in certain sense. So we had to tool in OpenEmbedded, and given the object-oriented nature of OpenEmbedded, we just had to write a CPC image class, and then inherit that class in our image structures. And that's where we are taking care of all our binary management. So there are other conventions of like what is a release build, what is a development build, and all those things are actually covered in there. So we did work with shared state. So shared state is kind of a pre-built management that's been recently introduced into OpenEmbedded. It's more for build acceleration, and it uses reference counts and does a checksum of the build dependencies and variables, and then use that to determine if something has changed in a component in order for it to rebuild. Otherwise, he will not rebuild it. So we have deployed the S-state caches internally. It was more of an infrastructure work. We haven't yet made it available across to every developer community because it's a lot of data. It's gigabytes of data. So you cannot shovel it across continents for build acceleration. So you have to have local mirrors. So far, where we have it deployed right now is in our auto builders. And we have a mechanism of, or we are working actually on a mechanism of creating snapshots and then having them available for offsites, and then eventually we would want to have mirrors on every site, which will be actually synced automatically over time. But we don't have that in place. The S-state cache has given us a lot of build performance improvements. Initially, when we had it, the builds were around 2 hours, 2 hours 30 minutes. With S-state cache deployed, our build times generally are somewhere between 15 minutes to 20 minutes. Our boxes are 8-core boxes with 16 gig of RAM, and they are running in VM. So I think if you throw more, faster I/O on that, then it gets even below 10 minutes. So it's pretty good with S-state. Component refactoring resulted in a lot of component refactoring, because what OpenEmbedded does is it has a component view of the things, whereas in RDK build we didn't. So a lot of the components, they had cross references. So you needed a header from a component, you just went ahead and -i and give that path, and you are okay. And with OpenEmbedded, it doesn't work that way, because it bakes a component in its own shell. So the only API reference it has is a sysroot. So what you have to have is all the interfaces, all the dependencies it needs, they have to be pre-built and they have to be staged. When we started porting RDK components more and more into OpenEmbedded build framework, we saw that a lot of components had this intricate interdependencies, where they were using each other, without even calling out dependencies on those. So it ended in a lot of restructuring of we creating libraries and staging the API headers, and in some cases we had to have two stages, where in one stage we stage just the APIs, in second stage we stage the libraries. So we try to break those hard dependency loops. But what it has done is it has also given a nice API interface into RDK, which now we will be exporting using Doxygen, and it will be updated, and it will be available on RDK LLC, so you can see the API interfaces and everything, and we are hoping that it will clean up and make it much more understandable now than before. So so development workflow, we did talk about it in the repo integration. It's we have tried to make it a lot more traditional workflow that people have. So if they are known to do make file builds and that mechanism, we have actually deployed OpenEmbedded underneath that kind of workflow. So what happens now is with repo, we have Garrett in backend. So you check out your sandbox, you make change, either it is in Yocto framework or it is in an RDK component, doesn't matter. It can be in any number of components. And then our repo is actually tooled. When you check it out, it knows where our Garrett is. So after that, you make changes, you commit them, you do repo upload, and then it figures out the remote, and it posts all your changes to our Garrett, and they appear on Garrett. Once they appear on our Garrett, we have verification builds. So we have a Jenkins build framework that is then triggered from Garrett. So it has dependency knowledge. So if you modified a certain layer, it only checks what all machines are affecting that particular component. Only those are built. And it posts those particular commits and then starts this verification builds, and its verification is all automatic. We can't commit unless the verification is positive. So which means we don't want to break our builds. So that's our primary criteria. We'll introduce more runtime tests. Yeah.
So you do pre-submission integration? You do continuous integration
yes.
at the time of pre-submission?
Correct.
Before committing it to the
yes.
development
yes.
launch?
Yes. So we want to move as much as testing as we can before the patch lands in the repository. So that's a more cheaper way and more accelerated way of doing your development. And right now we only do builds, but soon we want to accelerate it, and we want to make it to also be able to run smoke tests. So we have our emulator BSP. So we are working on some of the people in Kalyan's team and all. They are working on making sure that emulator can be launched in a non-interactive way. And so if that's possible, then we will launch, we'll spin the VMs on some target, run RDK in a emulator, run the, whatever smoke tests we have, and then the results will come back. So we'll have both build time and runtime smoke tests for every check-in that comes in. So one of the problem that we have right now is with Garrett. Actually, we have a solution for that, but it's a general deficiency in Garrett, is that you can't club commits across repositories. So if you make changes to 2 or 3 repositories, you can't verify them together. So that kind of defeats the purpose of verification build, because each one of them now goes out for individual builds and they each fail because all 3 are interdependent. So we have plans to actually enhance repo for that. Our engineers, they haven't yet started on it. But we have a solution that where we have tool Jenkins. Actually, you can specify the IDs of Garrett, IDs of these 3 commits. I want to verify them together. So you can launch, yeah.
So as part of your CI, are you also monitoring regressions for your boot time as well?
Not yet.
Okay.
Not yet, but soon.
When soon?
I think it depends. Like what we are looking at is there's also another problem of turnaround time. So when a developer uploads his patch, he wants quick turnaround.
Yeah.
So so we have to get our builds under 15 minutes. Then we have to start seeing how much we spend on the boot. Then I think the whole process, we want to get it in half an hour. And yeah, so I think we have things in place. It's just that we have to deploy it now. It's a matter of, yeah.
So when your situation that you describe actually is several repos, and then actually commit across several commits across them, don't you think it's just sort of like wrong in the first place? If they have actually very tight connection actually between each other, should be actually just one repo? Because atomicity actually of SCM actually kind of violated in this case anyway, right? So
Yeah.
even if you solve kind of like your validation actually problem, is still sort of, what if somebody pulls different kind of like reference point of those things? That's why we have SCM, that it's atomic, right? So it's kind of put the things in and you kind of pull it towards the right point.
Right. So I think you're talking about verification, right?
No, I'm talking about the whole situation.
Yeah.
Where you're committing in 2, 3 let's say 3 different papers, and kind of like each actually change, and they all actually interdependent. In my opinion, it's just a wrong actual architecture actually. So because you need to normally actually I would suggest actually to collapse all those actually 3 repo into actually one thing, and in this case actually you can do actually commit all 3 actually pieces goes actually to one actually SCM.
Yeah.
Because the validation is just the beginning of the problems when you have separate SCMs for pieces that kind of like have very tight connections. Right?
Yeah, but there are valid use cases. For example, when you move component, so like take an example of a meta layer, a Yocto, or any of the meta Yocto or whatever they call it. But let's take one example, right? You have a particular component that's lying in, let's take a different example. That's lying in our MSO layer, our Comcast layer, right? And then now it has been open sourced, right? So now it has to move from the Comcast layer to RDK layer. So, and there are images which are building it, right? So now you have to delete it here and you have to add it here simultaneously. And those are 2 different repos. So I agree that it will not be a common use case, but it is an often use case that we had to address. And yeah.
Yeah. So you told that in Garrett you have this issue of like grouping interdependent changes, and the Garrett has a topic feature. Isn't it good enough for your case? can basically mark a set of changes with some tag, and then you can pull all this, like, request, get a query with all these changes together. So you can basically tag the related changes in the Garrett.
Yeah, I think we could do that. That's true. I think what we were looking for more of a group ID that gets attached to the commit. So like it has change IDs, you have a group ID, and then it becomes easier to group together a bunch of commits without any of Git operations underneath. You just can look at the commit header and then make decisions. So basically, working with the change ID concept that was introduced. So like if you have changes in same repository which are more than one, they are locked to each other, so they can't go in atomically, right? Here, the problem is still there because now you can verify them together, but they have to be committed as well in atomic. We still don't have that solution. We still go and if there are 3 commits, we go and then they get committed individually, right? They are not attached to each other, even though we verified them together. So the good thing it would be that if Garrett had the group ID feature, where he knows that these 3 are cross repos, but they are related, and then they all can be committed atomically after all the validation and everything. So so there is still some work to do there. But I think what you are saying could work. We haven't experimented with it.
Yeah, I think, yeah. So the simultaneous commit is just addition to this topic feature, so you
Yeah.
should be able to extend it.
Is it across repositories?
Yes.
Okay.
Well, I mean, in the same Garrett instance, I mean, in the same Garrett server.
Right. Okay. Yeah, I think that will be something that I think we can investigate, but we were more like looking at adding a group ID feature on the same tone of change ID.
Is that also across like developers, or is it something that one developer has to push all the commits? Like,
No.
is it in your, so it's across?
If other developers push with the same
topic.
tag, it will share. So you can basically, for web interface, you can just click on this tag and it will show you all the commits across different repositories which are tagged.
It's good to know. KHEM, yeah, 5
Yeah.
minutes.
Okay, so I think so those are kind of things that were involved, and we had the release workflow as well. So that involves, like as I said, it was productizing this, getting into production, and there is a release workflow. There are release tools, there are tagging tools, branching tools, testing tools. They expect certain things from the system, and so there was a lot of changes that has to be made, not into OpenEmbedded in per se. There were some changes done into OpenEmbedded as well to generate information that was expected by our release tools. But there were also changes in the release tools themselves massively, in fact, to adopt to the new release models. So I think those were like kind of firmware nomenclature. We have, I did mention that we have a special naming convention for our firmwares. So we had to retool that into OpenEmbedded when it is generating the firmware images, and it's quite involved process actually, and it's very well supported by various tools across the whole release cycle. So those names, if they don't match, then hell breaks loose. And we were also suffering from some code bloat, and OpenEmbedded helped us with its tools. Actually, it has a tool that actually Kuhn wrote, and it's called now Build History, and that tool helped us a lot, because in Comcast we had our own methods of finding out code bloat and dead code, but that just tells us what are our top contenders for image size, and you can really attack those and then get below the limits that you had. So actually we were able to reduce the code size by at least 12% without much effort on using OpenEmbedded workflow. And these were new components, so usually newer components are bigger in size, whereas the older SDKs were using UClibc, which is supposed to be smaller, and it was not using systemd. So there were a lot of other kind of code bloat they had, which we had to throw away. If we were more featureful, we were less in size, so that's very strong. Yeah, so training and documentation, we did a lot of training. So it involves lots of training. So you have to go talk to the developers almost on a regular basis and keep taking their pulse, because they can rebel at any time. So, so these are new things, right? So the change is hard. And so we had to do a lot of training and a lot of documentation and a lot of case studies, talking to teams and understanding their use case. Everybody has their little own workflow, and they want to make sure that they are taken care of. So our Qt guys have their own way of doing things. XRE guys, so everybody has some nuances that they want to see how that is addressed in the new build framework. So that was a big chunk of the thing. So we did video trainings. We recorded them, and then people could watch them, and we did step-by-step screencasts, and we did write documents, procedure documents. So a lot of energy went into that. So there are some challenges with Yocto as well, and some of them are the developer workflow. We have solved it, but it still has issues. For example, it's very conservative when it comes to build. So if you have a direct dependency, he doesn't care. He just goes and rebuilds the component. So there is no inter-component analysis where he can find out there is no API change, so I need not build this component. So if a component has changed, period, all the dependencies are rebuilt, which is actually good because it gives you a consistent behavior, and it's very nice. But in the end, like, developers complain. Our use case is very specific because we use large components like WebKit. And then we have tied media framework directly into Qt. And media framework does change, which means if you change media framework, WebKit has to be rebuilt, and then all the dependencies thereafter. So your build compile cycle elongates to suddenly to like half an hour, 40 minutes. So we have that challenge, and we are looking at some concepts in OpenEmbedded that are there in newer versions. We are on 1.6, so newer versions have something called locked shared state. So we are investigating that, and we are actually hoping that we will be able to use it and provide it to our developers so they can selectively lock big components and then churn the smaller components without causing this rebuild churn, and get a faster code compile and debug cycle. So that's one of the big one that we are looking for. There are a few more, but so it's very resource intensive right now. Our builds with Yocto involves a lot of heavy machinery. Still, it's fast, but it requires resources. So we have identified certain build problems that we want to optimize. One of them is bitbake takes a lot of memory. So we have actually a project scheduled that our engineers will work on optimizing bitbake memory footprint, and also looking into if bitbake can work with Python 3 and give us better multi-threaded performance. Now that we have multi-cores, that's very important. So yeah, so I did talk about shared state. That's exactly what the enhanced pre-build support was, and paradigm shift in development. So we have all the developers, they say, why you are making our life, difficult? Because they know there is a way they are known to work with. You can call it efficient or not, but they know how to work with it. It's a known devil, and it's always, that known devil is better than an unknown angel. So everybody, they want to kind of know, they want to get comfortable. So it's a big challenge for us, and the patch management workflow is very, very scary for developers. It may not be as much for when you work on like open source and all the control mechanisms where you don't have a way to commit your code, but at places where you interact with the SCMs directly, they are patch mechanisms are foreign to them. So sorry. Adoption challenges, again, they are same. We have teams that we have to, and then upstreaming. We have problems with upstreaming because we have now collected a lot of changes to OpenEmbedded, and we have to figure out a way to upstream because we are not experienced upstreaming, and we have to work with legal as well, on our upstreaming path. Yeah, so this is the component Yoctoization. We have done some of them, but it still remains that there are, as we bring in more devices, the more components come in, and we have to go in and attack those components and make them buildable in OE. They are generally, you can build them, but we want to make them more scalable and have a nicer build framework. So we are taking this opportunity to also clean up the components and have their individual component build system to be strong. So yeah, I wanted to
Skip it.
yeah, so we actually had a wanted to show the tools that we have a portal tool which is our orchestration tool.
Maybe you can go to the web page.
Yeah, so
Chrome and just a minute. Yeah, Chrome. Yeah. Escape. Go to the first tab. That's RDK folder.
right. So this is our dashboard. So as you can see, like when the build goes through Jenkins, eventually they show up here, and you can do a lot of stuff actually here. And I'm trying to see if I have one of those Yocto builds.
Go up to the basics and
So it's a tool that analyzes the reports of Jenkins, the log.
Right.
of
So
Jenkins.
it's a tool that's written by.
yeah, click on at the bottom. You see basic XMP V2 Yocto build. Yeah, that below that.
Yeah. So yeah, for example, this is the build, and as you can see, it shows you how much time it took, 42 minutes.
See the older build framework took an average of 2 hours, 12 minutes for 426 builds, and Yocto is at 40 minutes for
Yeah.
the same order build. So you can see the performance improvement. And it's actually faster, but we had this issue, media framework and CEF, that was causing some problems.
Right, and then you can download the images, and it also tells you about all different formats that are downloadable, and you can also download an image directly into a set-top box.
Right.
So this is our orchestration tool when we were mentioning about booting. So this is the tool that we will utilize. So all the bolts are in place.
What do you call it?
It's called Portal.
Portal?
Yeah. And
It's open source and.
No, it's not open source.
No,
it's not open source.
Not yet.
SANJAY has tried very hard, and I don't know. I mean, probably it will be one day.
Yeah.
So far, it is not. And
And those are the test views. So some of the builds go through automated testing. Like we do quick test, and if you see, it says of what percentage of tests pass, like 83%, and you can go and look at the individual test results. You click on the click on that number.
yeah, so I think this is our orchestration. This is the kind of cockpit. So everything is reported here in the end, and you can basically also, I think you can deploy the images from here directly
Oh, yeah,
into
you can
into
deploy
the
and you
into
can
the
so
field.
this automated testing of builds.
And is it linked to the, requirement management or defect management?
Yeah, they're all linked to like if you go to the Garrett view, can you go to the Garrett view? Yeah. That shows the verification process. Like all the builds that go through Garrett show up here. So you can see how many builds, you can actually see how many builds were triggered.
Yeah, so I think there are thousands of builds that happen
Right.
per day because of verification builds, and and then there are regular nightly builds, and there are regular release builds and all.
Move
those.
to the right. You can see, so that's a change. And if you move to the right, further to the right, yeah, go down. Okay. Yeah, go down further. You see, now you have one build triggered, because if you go further down, I think you'll see some other devices that we're triggering like builds across. It depends on the dependency. Like here, we're triggering builds on all these devices because of that one change, because it impacts all of those builds. And if they fail, then we kind of flag that. You can click on like success, for example. Can you click on like success and or fail or something? It will take you to the build, and we've actually pulled all the Yocto logs into the portal, so you can see what is going on.
Right. So there is more to come. There are
So
more
you
Yocto tooling.
If you go down, you can compare any two builds, and you can see the change sets between the last successful build, and you can look at the manifest. So here, this is, if you click on success components above, you click on success on top.
Where?
On the top, the button, there's a button there. If you go further down, you'll see success. Yeah, it shows all the Yocto logs. You can go and, if it fails, it's more useful because we show the failure log, and you can go and look it up. The next thing we are doing is integrating with Toaster, so we'll see a Toaster view coming up soon.
Right. So we want to have a errors view actually,
Right.
where you can do error management, where it will show you a component by component, which component failed how many times, and so you can do all kind of statistics. So there is a lot of push towards deterministic builds, and we want to have statistics around that. Then all that can be tooled in here.
You're just
So I think
teasing everybody now.
So that's yeah.
I have a couple of questions. If you,
Yes,
if you-
please.
If you like. Yeah.
Yeah. Go ahead.
The first question, it seems to me that you have made various modifications. I didn't quite understand if it was to Yocto itself or adding your additional tools
For
some layers, like for instance for the.
yes, we have done modifications all across. So we have done modifications to
My
Comcast.
question is, have you contributed back this modification to the Yocto project? Or?
Some of them yes, some of them no.
Okay.
So large set of them are not yet contributed.
But this is your intention.
Oh yeah, absolutely. We
Yeah.
want to
Especially when you change something in
yes,
OpenEmbedded.
yes. So we actually want it other way around. So right now we have our master builds going. So actually we want to get into the master first, and then upstream it first,
Okay,
and then
good.
pull it into our stable. Like
And my second question is, I guess at Comcast you have, I don't know, thousands of developers
yeah,
which use different workstation,
yeah,
different Linux version.
yeah.
How do you cope with the host machine dependencies?
Yeah, I think the good thing about OpenEmbedded is it is consistent across many Linux distributions. So we
OpenEmbedded.
really don't care what they use as long as it's a sane kind of Linux distribution. Then-
OpenEmbedded is tested across
Yeah.
multiple. It works with Red Hat
But-
and SUSE. And
But we are also provisioning VMs in our build cloud to developers. So they can request a VM in our build cloud and use that for their work. So they are free to do that. We are getting more, our cloud is right now not as big, but we hope that as the developers ride the wave, it will get bigger, and they will actually be using consistent VMs actually for their workflow.
Okay, okay. My third question is, you explained that you have this external
SRC?
SRC,
Yeah,
source,
yeah.
source, yeah.
okay, which we can play with to bypass,
Fetching.
not chunk the fetch, unpack, and
Batch.
patches
Right,
steps.
yes.
So how do the integrators and developers, you have two different systems?
Yeah.
You have two
So-
different systems?
So what we do in our, so I mentioned about repo hook. So repo hook is invoked if you pass it an option. So if you pass it an developer option, it will create all that external SRC tree for you, and you can say don't do it. Then it goes back to the normal OpenEmbedded build framework. So SRC URI and patching and whatever is also encoded in the recipes, right? But so you have a choice to use it or not. And usually we always enforce the developer, the developer model.
But if I'm a developer, I will just do what you are
Yes.
explaining, and it's forever.
Correct.
Okay.
Correct.
So, question on external SRC URI. So it is per component, right?
It is per component, yes.
And kind of where do you specify? Is it possible to to specify like local code?
Yes. So we actually so in OpenEmbedded there are several configuration files that you can generate. So we generate a file called auto.conf. So this is actually this is the output of the repo hook that we have, post-processing hook. So it generates a auto.conf, and it has all the lists actually of all the the components and telling it where to look for the sources.
So it's like external SRC URI underscore bash.
Right. Yeah, it's a generator, and I don't know the details. So
we can show them auto.conf. You go to any build, you can see that. You go to a Yocto build.
Oh, on Jenkins?
Yeah, go there and click on the first one. Yeah, click on that.
Yeah, I think it's still like elastic, so components are added and deleted, and sometimes we do have issues with repo. So when you try to do that on Jenkins node on single repo, it gets confused sometimes when you add a new component, but most of the time it works fine.
Go to the success not there. Click on like the first upstream. Click on that guy. And then artifacts. You should see it there.
Oh, it is in the artifacts?
Yeah, it's in the artifacts. We have some performance issues right now with Jenkins. It's a little bit slow. Usually it's not that slow.
It's probably on the other side of the world as well.
Right. Build artifacts, you should see auto.conf.
Right. So this file is generated by the post-processing hook.
Yeah, you see the manifest too.
Oh, I think I need to say view.
Yeah.
Yeah, so this is actually the list of all components here, as you can see. So it just specifies, what the SRC rev is and what is the SRC URI, where to look for it, like the external SRC here. So some of the build rules we have to enforce for this, of course, that we can't have patches for RDK components. So because if you have patches, then this doesn't work. So
and this one is actually already in OpenEmbedded, right? So it's
correct.
It's a standard feature.
Correct.
So in Comcast, do you have given the size of the deployment, you have a team fully supporting OpenEmbedded for the developers?
Yes.
Yeah, that's him right there.
Yeah, we
That's
have a
him
team
right there.
You are. How many
That's
of
the
you
team.
are there?
We have a team of around
We have
around close to 10 people.
We have like
focused on
team which is working on various functions. So right now they are
maintaining the framework and
yeah. Altogether the team there are around 25, like including the tools, like because we develop all the. So we have one team that works on the build, like just the basic build, like Yocto, migrating components, writing recipes, and we have another team of around 10 to 12 guys that just focused on all the tooling, like putting together the portal and
Jenkins, plugins, and all of that. So it's a quite a big team. And we have a 5-member team working on the emulator. And all it does is, it's just it's like to use to validate the RDK. So Kalyan is the lead of that team.
All right, thank you very much.
Thank you. Very interesting.